This is a transistor. It's one of the most important devices ever to be invented. So we're going to learn how they work in detail in this video. Transistors come in many shapes and sizes. There are two main types, the bipolar and the field effect. We're going to mostly focus on the bipolar version in this video. Transistors are small electronic components with two main functions. It can act as a switch to control circuits, and they can also amplify signals. Small, low-power transistors are enclosed in a resin case to help protect the internal parts, but higher power transistors will have a partly metal case, which is used to help remove the heat which is generated, as this will damage the components over time. We usually find these metal body transistors attached to a heatsink, which helps remove the unwanted heat. For example, inside this DC bench power supply, we have some MOSFET transistors which are attached to very large heatsinks. Without the heatsink, the components quickly reach 45 degrees Celsius, or 113 degrees Fahrenheit, with a current of just 1.2 amps. They will become much hotter as the current increases. But for electronic circuits with small currents, we can just use these resin body transistors, which do not require a heatsink. On the body of the transistor, we find some text. This will tell us the part number, which we can use to find the manufacturer's datasheet. Each transistor is rated to handle a certain voltage and current, so it's important to check these sheets. Now, with a transistor, we have 3 pins, labeled E, B, and C. This stands for the emitter, the base, and the collector. Typically, with these resin body type transistors with a flat edge, the left pin is the emitter, the middle is the base, and the right side is the collector. However, not all transistors use this configuration, so do check the manufacturer's datasheet. We know that if we connect a light bulb to a battery, it will illuminate. We can install a switch into the circuit and control the light by interrupting the power supply. But this requires a human to manually control the switch. So how can we automate this? For that, we use a transistor. This transistor is blocking the flow of current, so the light is off. But if we provide a small voltage to the base pin in the middle, it causes the transistor to start allowing current to flow in the main circuit. So the light turns on. We can then place a switch on the controlling pin to operate it remotely, or we can place a sensor on this to automate the control. Typically, we need to apply at least 0.6 to 0.7 volts to the base pin for the transistor to turn on. For example, this simple transistor circuit has a red LED and a 9-volt power supply across the main circuit. The base pin is connected to the DC bench power supply. The circuit diagram looks like this. When the supply voltage to the base pin is 0.5 volts, the transistor is off, so the LED is also off. At 0.6 volts, the transistor is on, but not fully. The LED is dim because the transistor is not yet letting the full current flow through the main circuit. Then, at 0.7 volts, the LED is brighter because the transistor is letting almost the full current through. And at 0.8 volts, the LED is at full brightness. The transistor is fully open. So what's happening is we're using a small voltage and current to control a larger voltage and current. We saw that a small change to the voltage on the base pin causes a large change on the main circuit. Therefore, if we input a signal to the base pin, the transistor acts as an amplifier. We could connect a microphone which varies the voltage signal on the base pin, and this will amplify a speaker in the main circuit to form a very basic amplifier. Typically, there is a very small current on the base pin, perhaps just 1 milliamps or even less. The collector has a much higher current, for example 100 milliamps. The ratio between these two is known as the current gain, and uses the symbol beta. We can find the ratio in the manufacturer's datasheet. In this example, the collector current is 100 milliamps and the base current is 1 milliamp. so the ratio is 100 divided by 1, which gives us 100. We can also rearrange this formula to find the currents also. We have two main types of bipolar transistors, the NPN and the PNP type. The two transistors look nearly identical, so we need to check the part number to tell which is which. With an NPN transistor, we have the main circuit and the control circuit. Both are connected to the positive of the battery. The main circuit is off until we press the switch on the control circuit. We can see the current is flowing through both wires to the transistor. We can remove the main circuit, and the control circuit LED will still turn on when the switch is pressed, as the current is returning to the battery through the transistor. In this simplified example, when the switch is pressed, there are 5 mA flowing into the base pin. There are 20 mA flowing into the collector pin, and 25 mA flowing out of the emitter. The current therefore combines in this transistor. With a PNP transistor, we again have the main circuit and the control circuit, but now the emitter is connected to the positive of the battery. The main circuit is off until we press the switch on the control circuit. We can see with this type that some of the current flows out of the base pin and returns to the battery. The rest of the current flows through the transistor and through the main LED and then back to the battery. If we remove the main circuit, the control circuit LED will still turn on. In this example, when the switch is pressed, there are 25 mA flowing into the emitter, 20 mA flowing out of the collector, and 5 mA flowing out of the base. The current therefore divides in this transistor. I'll place these side by side so you can see how they compare. Transistors are shown on electrical drawings with symbols like these. The arrow is placed on the emitter. The arrow points in the direction of conventional current, so that we know how to connect them into our circuits. To understand how a transistor works, I want you to first imagine water flowing through a pipe. It flows freely through the pipe until we block it with a disc. Now, if we connect a smaller pipe into the main one and place a swing gate within this small pipe, we can move the disc using a pulley. The further the swing gate opens, the more water is allowed to flow in the main pipe. The swing gate is a little heavy, so a small amount of water won't be enough to open it. A certain amount of water is required to force the gate to open. The more water we have flowing in this small pipe, the further the valve opens and allows more and more water to flow in the main pipe. This is essentially how an NPN transistor works. You might already know that when we design electronic circuits, we use conventional current. So in this NPN transistor circuit, we assume that the current is flowing from the battery's positive into both the collector and the base pin, and then out of the emitter pin. We always use this direction to design our circuits. However, that's not what's actually occurring. In reality, the electrons are flowing from the negative to the positive of the battery. This was proved by Joseph Thomson, who carried out some experiments to discover the electron and also prove they flowed in the opposite direction. So, in reality, electrons flow from the negative into the emitter and then out of the collector and the base pin. We call this electron flow. I'll place these side by side so you can see the difference in the two theories. Remember, we always design circuits using the conventional current method. But scientists and engineers know that electron flow is how it actually works. By the way, we have also covered how a battery works in detail in our previous video. Do check that out, links can be found in the video description down below. Okay, so we know that electricity is the flow of electrons through a wire. The copper wire is the conductor and the rubber is the insulator. Electrons can flow easily through the copper, but they can't flow through the rubber insulator. Inside the transistor, we have the collector pin and the emitter pin. Between these, in an NPN transistor, we have two layers of N-type material and one layer of P-type. The base wire is connected to the p-type layer. In a PNP transistor, this is just configured the opposite way. The entire thing is enclosed in a resin to protect the internal materials. When we connect a voltage source across the two ends, with the positive connected to the p-type material, this will create a forward bias, and the electrons will begin to flow. The voltage source has to be greater than the 0.7 volt barrier, otherwise electrons cannot make the jump. When we reverse the power supply, so that the positive is connected to the n-type material, the electrons held in the barrier will be pulled back towards the positive terminal and the holes will be pulled back towards the negative terminal. This has caused a reverse bias. In a NPN transistor, we have two layers of n-type material. So we have two junctions and therefore two barriers, so no current can flow through it ordinarily. The emitter n-type material is heavily doped, so there are a lot of excess electrons here. The base p-type is lightly doped, so there are a few holes here. The collector n-type is moderately doped, so there are a few excess electrons here. If we connect a battery across the base and the emitter, with the positive connected to the p-type layer, this will create a forward bias. The forward bias causes the barrier to collapse as long as the voltage is at least 0.7 volts. So the barrier diminishes and the electrons rush across to fill the space within the p-type material. Some of these electrons will occupy a hole, and they will be pulled towards the positive terminal of the battery. The p-type layer is thin and was lightly doped on purpose, so that there is a low chance of electrons falling into a hole. The rest will remain free to move around the material. Therefore, only a small current will flow out of the base pin, leaving an excess of electrons now in the p-type material. If we then connect another battery between the emitter and the collector, with the positive connected to the collector, the negatively charged electrons within the collector will be drawn to the positive terminal, which causes a reverse bias. If you remember, with the reverse bias, the electrons and holes of the barrier are pulled back across. So the electrons on the p-type side of the barrier are pulled across to the n-type side, and the holes on the n-type side are pulled back to the p-type side. There are already an excess number of electrons in the p-type material, so they will move to occupy these holes, and some of them will be pulled across, because the voltage of this battery is greater, so the attraction is much higher. As these electrons are pulled across, they flow into the battery, so a current develops across the reverse bias junction. A higher voltage on the base pin fully opens the transistor, which means more current and more electrons moving into the p-type layer. Therefore, more electrons are pulled across the reverse bias. We also see more electrons flowing in the emitter side of the transistor compared to the collector side. Okay, that's it for this video, but to continue learning about electronics engineering, click on one of the videos on screen now and I'll catch you there for the next lesson.